Alright, so we're starting kind of our last chapter here with circles. Lots of properties about circles, lots of vocabulary about circles. Okay, we've done a little activity already with the vocabulary. So now just a couple notes for you. The first theorem that would be good to know, the book calls it Theorem 10.1. I don't care that you know the number of it, but just so you know where I'm coming from in the book. Basically, in a nutshell, it says a tangent line is perpendicular to the radius of a circle at its point of intersection. A tangent line is perpendicular to the radius of a circle at its point of intersection. Alright, so a little picture to go with that. If I have a circle, and I draw a tangent line, why is that a tangent line, first of all? Only hits the circle at one point. Just nicks it, just grazes it. Okay? So let's say that point of intersection is located right there. Okay? So this is a tangent line. Well, what I know then is that if I draw the radius, so here's my tangent line. Here's my radius of the circle. Okay?
There's 90 there.
There's a 90-degree angle right there. Yep. That is a 90-degree angle right there. That's all that Theorem 10.1 is saying. Okay? A tangent line to a circle is perpendicular to the radius that intersects the tangent line. Only that radius, right? I mean, because I could draw another radius. You know, that's still a radius up there too, right? That radius clearly is not perpendicular to this tangent line. Okay? The radius that touches that point of intersection, that radius is perpendicular to the tangent line. Okay? Okay, so a little application of this theorem. Let's say the red circle is some planet way out in outer space. Okay? And we are located right here with a satellite, okay, or some sort of telescope. We want to know how big this planet is. Okay? Well, clearly I am not going to go to the planet and measure what its radius is. But if I could calculate the distance from where I'm at to where my tangent line would just intersect the edge of the planet, and then I would figure out the exact length, again, to the edge of the planet right here, I think I could figure out the radius of that planet. What type of triangle is this?
Right.
A right triangle, because isn't this right here a 90-degree angle? Everybody okay with that? Because that's a right triangle, what theorem always works? Pythagorean's theorem. So wouldn't it be true that 20 squared plus r squared equals whatever 15 plus r squared is? Does that make sense? A squared plus b squared equals c squared? You think I could solve this equation for r? Absolutely. 20 squared is 400. R squared is simply that, r squared. And 15 plus r squared, I'm going to actually have to take 15 plus r times 15 plus r and FOIL that out. So 400 plus r squared equals 225 plus 15r plus 15r plus r squared. I just FOILed that, right? You guys have done that in algebra? 15 times 15, 15 times r times 15, r times r. Okay? I'm going to subtract r squared from both sides. That's convenient. They're both gone then, right? I got nothing left on the r squareds. So then I have 400 equals 225 plus 30r. Because my r squareds were gone. 15r and 15r makes 30r. And again, the r squareds were gone. Subtract the 225 and then divide by 30, right? Subtract 225, so that'd be 175 equals 30r. Divide both sides by 30, and you get 5.83 repeating.
Yep.
Okay. So I just figured out the radius. You know, maybe we're measuring in thousands or 100,000s or, you know, I don't know, so I know it's not really to scale, obviously. But I could figure out the value of r just using those indirect measurements and some geometry skills. Okay? So any questions on that? Okay? And then the last thing, the last theorem, I'm not going to write it out, I'm just going to draw a picture of it. If you have a circle, and you have a common point somewhere outside the circle, how many tangent lines could you draw that go through this point? 2. One would kind of hit the top of the circle like this. Okay. And the other one would hit the more the bottom edge of the circle. Right? Obviously, if I keep going, it's not going to intersect anymore. So let's just call these tangent segments or whatever. What do you think is true about the length of AB and AC?
They're the same.
They're the same. Okay? AB is congruent to AC. They're the exact same length. Theorem 10.2 says, tangent segments from a common external point are congruent. So these are called tangent segments, not tangent lines, because they don't go on forever, alright, they just stop. But that tangent segment and this tangent segment would be exactly the same length. Okay. And then actually, to go a step further with this, I don't know if it'll show up in any of your homework, but it kind of makes some sense. That's a radius, right? What do we know about the radius and a tangent?
Makes 90.
That makes a 90. Wouldn't those also make a 90, assuming my picture is drawn to scale?
Yeah.
Okay? And if these two lengths are the same in blue, and those two lengths clearly are the same in red, what type of quadrilateral is that? Kite. Yeah, it's a kite. This would be 90, this would be 90. Alright, and you got a kite. So, that's theorem 10.2. Any other questions that you guys can think of right now? Okay, so you should be able to do page 655, 3 through 10, 12, 13, 19, 21 through 24, and 37. That's your first assignment in our last chapter.